All right, just another reminder, check out our SDAA YouTube channel. I love that picture of Ken. Ken, I don't know if you're on tonight, but I like that shot of you at your ASIG meeting, looking sharp. Check it out, over 455 subscribers, nearly 75,000 views. And tonight's meeting, with the permission of our guest host, is being, our guest speaker is being recorded. So for those of you who are not watching it live, or those of you who are watching it live and it is so good and you want to watch it a second time, it will be posted to our YouTube channel shortly. Check it out, and Dave will put that link for you in the chat. All right, one more video.
There is evidence that a planet around a distant star lost its atmosphere, then gained a second one through volcanic activity, according to scientists using NASA's Hubble Space Telescope. The planet, GJ 1132b, is hypothesized to have begun as a gaseous world with a rocky core. Starting out at several times the diameter of Earth, this so-called sub-Neptune quickly lost its early hydrogen and helium atmosphere due to the intense radiation of the young hot star it orbits. Then, the planet was stripped down to a bare core about the size of Earth, and that's when things got interesting. To the surprise of astronomers, Hubble observed an atmosphere which, according to their theory, is a secondary atmosphere that is present now. Based on a combination of direct observational evidence and inference through computer modeling, the team reports that the atmosphere consists of molecular hydrogen, hydrogen cyanide, and methane, and also contains an aerosol haze. Scientists think hydrogen from the original atmosphere was absorbed into the planet's molten magma mantle, then slowly released through volcanic processes to form a new atmosphere. Though this hydrogen continues to escape into space, the secondary atmosphere is replenished by volcanic gases that seep through cracks in the planet's thin crust. Scientists are wondering how many other planets might have started out as gas giants but became smaller and rocky after their early atmospheres evaporated away. Astronomers hope to use the upcoming James Webb Space Telescope's infrared vision to detect hot areas of volcanic activity on the planet. GJ 1132b might be orbiting a distant star 41 light-years away, but thanks to the Hubble Space Telescope, it just got a little bit closer.
All right, we are getting very close to starting our main feature tonight, Dr. Mike Ressler. As a reminder, what we are going to do first, though, since we are not in person, hopefully soon, but not quite yet, is we have our digital door prizes. So tonight's digital door prize, you can get the link there off the chat, is not 5, not 6, not 7, not even 7.5, but 8 full hours of NASA's deep space scenery, complete with music. I'm going to give you a quick preview of this video that you can link to and watch for free. We're not going to do the whole thing, obviously, because it's 8 hours long, so we'll just do the first couple hours. Dennis Amon, you're getting sleepy, very sleepy. All right, I think you get the feel for that. And hopefully, Dennis, you are now awake. Okay, with that, you are about done having to hear from me, and we'll be listening to Dr. Ressler give his presentation. I will stop sharing my screen in just a moment. I'll let you read up a little bit on Dr. Ressler if you haven't already. One of the most interesting things about his career that I'm going to tell you, hopefully I'm not stealing too much of his thunder, is that he was on the group that wrote the proposal for the James Webb Space Telescope in 1994. So he was part of the concept, and it was approved, as you know. And he's been part of the development and the production, and very soon to be the launch. And that is an amazing thing, considering the cycle that spacecraft take. So that is, I thought, a fantastic thing to know about his career. He has seen this thing literally from soup to nuts, which I think is really fantastic. We will obviously have a question and answer period. If you have a question you're dying to want to know earlier, you can drop it in the chat and he may be able to answer it. If not, we'll be opening it up to you to speak with him, or you can drop it in the chat at the end. I'll give you one spoiler alert. As soon as I heard Dr. Ressler was this award-winning scientist at JPL, I thought, ugh, you must know the TV show The Big Bang Theory. So I got to ask, have you met anyone who's like Sheldon Cooper there? And Dr. Ressler was very polite. And he said, you know, Mike, I have never watched The Big Bang Theory, and I really don't watch a whole lot of television. And that would explain why he is a NASA exceptional scientist. He is a JPL research scientist, and I am not. So with that, I will stop sharing my screen and invite in Dr. Ressler to please share his.
Okay, good evening. So first question, can everyone hear me okay? The reason I have to ask is that even though we did a dry run Monday night to make sure that my computers would talk to Zoom and the gang there, the link tonight apparently requires me to log into Zoom, and that's actually prohibited on my JPL laptop that I was planning to use to share the presentation. So I do have a personal account on my own desktop, but nothing is the way I had expected it to be. So we'll give this a try and see how it goes. So if we're lucky, this will actually work. Okay, so I can't tell if I'm sharing this. So can someone perhaps give me a thumbs up that you can see my title page?
You're good, Mike.
Looks good.
You're all good.
Okay. Fingers crossed, here we go. Okay, so obviously I'm here to talk about the James Webb Space Telescope, but I'd like to start by talking a little bit about Hubble. And I was actually pleased to see one of the videos that you showed had my very good friend Jennifer Wiseman featured in it. So that's a good start, even if nothing else is going to work right tonight. Anyway, Hubble has really transformed the way we see the universe. It's been very, very productive and truly revolutionary. And occasionally it does some fun stuff for us. Come on, there we go. So every now and then it throws us a surprise. We look at it and we kind of smile and say, hey, that's kind of cool. The universe is putting on a nice show for us. But images like this are important, not just because they make us laugh a little bit, but we can learn an awful lot about what's happening just by what we see here. So the yellowish fuzzy blobs are galaxies that are relatively nearby. The important thing is they actually lie between us and galaxies that are much more distant. So the things that form the smiley mouth, the very blue colored things that you see are much more distant galaxies that the gravity from the yellow galaxies, magnify. They're so-called gravitational lenses. And this is important because the universe is giving us a way to see objects that are much farther away, much fainter that we wouldn't be able to see otherwise. And so even though those background galaxies are blurred by the gravity of the nearby galaxies, people who are much smarter than I am can mathematically reconstruct what those distant galaxies would actually look like if they weren't distorted. And we can see galaxies very close to the beginning of the universe as they're in the process of forming. So these sorts of things are hugely important, and Hubble really opened the field for letting us study these sorts of things. Another thing that Hubble has done, and in fact that previous image came from it, but it's picked out what we thought were relatively blank areas of sky and has spent countless hours just pounding on these same fields. So this is one of the Hubble ultra deep fields. And we can see that even though we thought it was relatively blank based on what ground-based telescopes told us, there's a large amount of stuff in there. And occasionally we'll find little nuggets like this fuzzy looking blob, GNZ11, is still the most distant galaxy that we've ever discovered. It's at a redshift of about 11.1, and the Keck telescopes on the ground were actually able to get a spectrum so that we know that the redshift really is 11.1. There are other techniques for trying to estimate redshift, but this one really has it nailed. So Hubble has really allowed us to go deep, find out what's on those far fringes of the universe. It's also produced a lot of really beautiful pictures. This is probably my favorite Hubble picture. It's the so-called Twin Jet Nebula. It's a star that's in the last phases of its life and is blowing out these beautiful streamers of oxygen and nitrogen and everything else that each show up as a different color. And I don't know if you can see my cursor with the way things are going. You see the big diffraction spikes from the central star, but there are also these sort of little, petals that come out from the central star. There's, just lots of really neat little details. And it reminds us that no matter how well we think we understand something, the closer we look at it, the less we know. And so it produces, an endless cycle of questions. What's going on here? How does this form? So it's really intriguing as we try to look at these things and understand what's happening. Now, there's another space telescope I need to talk about just a little bit, and that's the Spitzer Space Telescope. Spitzer Space Telescope is an infrared telescope that was launched in 2003. It ran out of coolant in 2009, so it had a 6-year lifespan. But as it turned out, a couple of the detectors could actually operate even though it had run out of cryogens. And so they didn't actually shut it off until just last year. So it had a 17-year career looking at the infrared skies. This is also a deep field, and all the little red dots that you see in this image are very distant galaxies. You actually see more of them, I think, in this Spitzer Space Telescope image than you did in the Hubble image, simply because they're far away, they're redshifted, and so they're actually brightest at infrared wavelengths rather than visible wavelengths. But just in case you're curious, infrared pictures can also be very beautiful. I know there are a lot of bad movies from the 80s and 90s that had a little bit of infrared imaging that were really terrible, like The Predator with Arnold Schwarzenegger. But we can get a lot of beautiful stuff from the infrared with our space-based telescopes. So this is a particular star forming region. I've forgotten which one exactly, but this was nicknamed the fountains of creation because it looks like fountains of water bubbling up in the image. So, lots of good stuff. So the Webb Telescope, and I know I'm going to call it James Webb way too often. We're not supposed to call it that. It's the Webb Telescope. Is really a follow-on to both of those telescopes, to both Hubble and Spitzer. And the questions that it's trying to answer are really questions that were raised by what we learned from both Hubble and Spitzer. Hubble and Spitzer answered a lot of questions, but they asked even more. And so Webb is supposed to allow us to start addressing some of those questions. So there are 4 main science themes to look at the first light-emitting objects in the universe. We saw all these little distant galaxies in the Spitzer image and so forth. So what were the first ones? Can we see back far enough to where the first stars and galaxies were just trying to form? Understand how those first galaxies were assembled. Did they start as little sort of amorphous patches of stars that coalesced into galaxies, or did we have massive disks of gas and dust that formed the trillions of stars that are in a galaxy? Then we want to look at how stars are born and planets are formed around the stars. And then finally, if we can, trace the evolution of planets and how the conditions for life may have been set up. So those are the big grand questions that we're trying to get to. Pardon me. So just a quick comparison before I get into far more of the details. The Hubble Space Telescope has a 2.4 meter diameter mirror. Webb is about 2.5 times bigger, so 6.5 meter diameter. And in some of the talks I give at JPL, I actually compare the Webb Telescope to an Imperial Star Destroyer, but not tonight. That'll have to wait for another time because they look awfully similar. But I want to reemphasize the Webb is not a replacement for Hubble. Actually, we hope that Hubble will go a few more years and that there'll be some overlap so that they'll complement each other. It extends what Hubble's done, what Spitzer has done. But what this means is that the Hubble or that the Webb telescope really needs to work at infrared wavelengths. And so the next couple of sections here might be very simple for some of you. Maybe for others, it's new material. So I'd like to actually take my time and explain it. Even if you've seen it a million times, I think the pictures are really cool and I don't get tired of it, even though I've been doing this for way too many years. So what is the infrared? If we look at a spectrum of white light, we get a very nice rainbow, but humans being inquisitive creatures might say, well, what's here just past the violet colors that we see? What's on the other side? What's just past the red colors? Well, William Herschel asked exactly these questions in 1800, and he tried to measure the temperature of the various colors by putting a thermometer, in the red, in the green, in the blue. And what he found was that the warmest temperatures were measured about where I have the what's here on the left side. There was radiation past the red, infrared below the red. That's where the majority of the energy was. And that was the discovery of infrared radiation. We can use infrared radiation to get a different view of the universe around us. So here's some nice little meerkats. This may have actually been down at the San Diego Zoo, I'm not sure. But visible wavelengths is very familiar looking. If we look at them with a thermal infrared camera, we start to see heat from these little critters. And what you'll notice is the bright spots that you see kind of on their chests. That's where their fur is the thinnest, so we're able to see closer to their skin where it's warmer. Also, their eyes are very bright, meaning that the eyeballs themselves are a bit warmer because they're in their head. They're more insulated from like their toes and feet, which are dark, so they're relatively cooler than the rest of the animal. So thermal infrared gives us a different view of temperatures of things. Another thing that we can use the infrared for is to see through particles, like particles of smoke or particles of dust. This is an image of a firefighter in a smoky room. If he only has his eyes to use to search for danger, he can miss a lot of things because he can't see very far through the smoke. But in the infrared light penetrates that dust and smoke, and we can see there's actually a person on the floor that needs help. And so thermal infrared cameras are actually a very common firefighting tool for exactly these reasons, to look for hot spots, but to also look for people who might be in the room. Well, we can use both of those properties in astronomy. This is an image of a little dust cloud that's floating around near the center of our galaxy, B68. For any of you with big telescopes, might want to try to look at it sometime. At visible wavelengths, the cloud is quite opaque, and we don't see any of the background stars through it. But if we look at it at near infrared wavelengths, it's the same as the smoke. All the dust particles that are in the gas cloud, infrared light can pass through it, and we can see the background stars now. And in fact, there's not a lot going on inside that cloud. So it's pretty easy to see through. There are other areas, though, where we get a lot of surprises. So this is a picture of a star field in Cassiopeia. And if you notice, everybody immediately sees the red thing here, but that's actually one of the least interesting objects in this field from my perspective. If you notice some of the dark bands and clouds on the left side of the image, This is where there are these star-forming clouds of gas and dust, and we can't see into them because they are so dusty. But when we go into the infrared, all of a sudden things start to pop out. And so all those reddish and purplish sort of things are very young stars that are still in their process of formation. And so if we want to understand how stars form, we need to be able to observe them in the infrared. On the right-hand side, you see a patch that didn't change. It's still the visible wavelength image. At the other end of the stellar life cycle, when stars blow off their outer layers, sometimes those outer shells are so cool, we can only see them at infrared wavelengths. So something you wouldn't have even known was there at visible wavelengths shows up as this bright, cool red shell in the infrared. So it really is a different way to look at the universe. It tells us a lot of things that we don't get from visible wavelengths. So those are all images in the infrared, and I need to talk a little bit about spectroscopy because that's a key ingredient of what the Webb Telescope will allow us to do. So, I showed that picture. If you shine white light into a prism, you get a nice rainbow. Well, if you have a tube of hydrogen gas that's glowing, like the picture on the left there, and I look at it through a prism, rather than a full color spectrum, full color rainbow, I get these bright lines. It's basically an image of the tube at different wavelengths. And so for some reason, I only see the tube at red, I see the tube at a kind of a cyan color, and I see the tube at a couple of purple colors. Well, these are emission lines. So the hydrogen gas emits light only at very specific wavelengths. And so, by a method I'll explain in a minute, we can measure the wavelengths of those lights. So hydrogen has these emission lines at 656 nanometers, 486, 434, et cetera. It's an interesting fact that a hot gas will emit light at those specific colors, but if you have cold hydrogen gas that's sitting in front of a white light source like a star, hydrogen will absorb those same wavelengths. And so there's, no matter whether the hydrogen is hot or whether it's cold, it still emits at the same wavelengths. And so we can use that as something of a fingerprint. If we see those wavelengths, we know we've got hydrogen. And in fact, every element has a unique signature. So helium has emission lines at different wavelengths, lithium, oxygen, and all that. And so we can use this to study the composition of a source. And if we look at our sun, we'd see a spectrum that looks like this. And so we see lines all over the place. There's a big absorption here at this red part of the spectrum. Well, there's our friend hydrogen. So we know that the sun has a lot of hydrogen in it because of how prominent that absorption feature is. And the numbers depend a little bit on who you're talking to, but in round numbers, our sun is 92% hydrogen, about 7.8% helium, and about 1/10% of everything else. We actually have detected about 69 elements in the sun's spectrum. So that's a lot of everything else in that 0.1%. But this is a technique we can use to find out what stuff is made of. The other thing about spectra is we can use it to determine how fast things are moving. So in the laboratory, in the bottom plot there, we see the wavelengths at their standard, what we call rest wavelength. They're not moving with respect to us. But as we look at stars or nearby galaxies, we see those lines starting to move to the right. Until we get to very distant galaxies, they've moved so far, you might not actually recognize them at first. But if we look for those same patterns with the right spacing, we can say, hey, that's hydrogen, but it's redshifted by a factor of 3. That means this galaxy is actually very far away, and it gives us a way of measuring distances in the universe That's actually more accurate than trying to figure out how many kilometers or how many light years. And so it's very common for astronomers to say, well, it's at a redshift of 8 or something like that. That tells us how far away things are from us. So we can use spectroscopy for lots of different things. So unfortunately, as much as I love rainbows, they're actually not very practical for analysis, for when we're trying to do quantitative measurements. And so we use plots instead. So the plot at the bottom is just a graphical representation of the rainbow above. So anywhere that's bright, we see that little line jumping up. And so that's what we normally do for visible wavelength spectroscopy. And we absolutely have to do it in the infrared because we can't see infrared. So as an example, this is a very young star. It's HH47. It's like many young stars, it's kind of messy and burps up lots of material and all that. But if we want to try to figure out what it's made of, because we can't see it at visible wavelengths, we do it in the infrared and see what's there. And so this is the spectrum. So that big dip right in the middle, silicates, that's basically kind of a rocky dirt, very common on Earth. Go outside, scoop up a hand, you'll get plenty of silicates. So it's a very common mineral, and because I keep talking about dust, it's kind of what we expect to see. We also notice that there's some water ice there, and methyl alcohol, and probably some other alcohols as well. Carbon dioxide is very prominent, and there's just a little bit of methane gas there. So as a good scientist, I immediately conclude that there are cows in space. Okay, maybe not. But the point of this is water, methane, carbon dioxide, these are what we call biogenic materials. So if we are looking for conditions where life could form, we want to see the material that makes up life. And so these are all sort of precursor molecules. These are molecules that you need to have life as we know it, at least. And so the fact that we're finding them around stars that are still forming tells us that the conditions or the material needed is actually pretty common. Doesn't tell us whether we actually have life, but at least allows us to understand whether the conditions are there. So that's what we're after and what we're looking for. So is there a question there? Or just a little bit of background noise? I'm happy to take questions as we go. We'll certainly do them at the end, but if there's something pressing, go ahead and give a holler. Okay, so actually a couple of video clips we watched before I started my talk were on exoplanets. It's the very, very hot topic right now. There's a little bit of a pun in there, but one of the things we definitely want Webb to do, and that Spitzer allowed us to start doing, is to look at stars with planets as the planet transits, goes in front of the star or is eclipsed by the star. Because when they're not in eclipse or not in transit, the light that we see is actually coming from the star and the planet together. So in this figure, sort of the starlight makes up the bottom, and then the planet light is a little bit extra on top of the star, on top of the starlight. When the planet crosses in front of the star, it blocks out a little bit of the starlight, and the overall brightness drops. But when the planet goes behind the star so that the planet is eclipsed, we only see starlight. So that's how we know planets are there. That tells us some basic properties of the orbits and stuff. But if we're fortunate enough to see changes in the planet light in the orbit, that can actually tell us about the temperature of the planet itself. So when we're looking at the planet when it's in front of the star, that means we're seeing the dark side of the planet, presumably the cooler side of the planet. And so in the infrared especially, there'll be a little bit less planet light. But as the star then comes around and it's on the opposite side, farther away from us, on the backside of the star, so to speak, we're looking at the sunlit side. and it will actually be warmer. And so it gives us that curve shape, and that allows us to say something about the temperature of the planet. We can use that same eclipsing thing if we get the spectrum of the star plus the planet, and then again during a transit where we only see the star, we can subtract them and actually get the spectrum of the planet by itself. This is actually how we discovered that Pluto and Charon had very different surfaces. We got a spectrum of Pluto and Charon together, and then when they were eclipsing each other, we got a spectrum of Pluto by itself. We subtracted them and said, hey, Charon has lots of water vapor that Pluto doesn't have, or lots of water ice that Pluto doesn't have. So we can do exactly the same thing with stars and their planets. So Spitzer was not able to do true spectroscopy. It could only get relative brightness at several wavelengths. We think Webb will actually allow us to get that full blue background spectrum. And so we'll actually be able to study the atmospheres of planets around other stars as a result. And so if we can do that, that'll be, a huge thing. So one of the things we're definitely looking forward to. Okay, so hopefully I convinced you that observing at infrared wavelength is really neat. So if it is so neat, then why doesn't the World Plus dog have an infrared telescope in their backyard? Why can't you just stick one out in your backyard and join in the fun? Well, there are three problems. First is room temperature emission, and I will explain all these in gory detail in just a second. Another is our Earth's atmosphere isn't overly cooperative. And finally, the detectors themselves have some issues. So room temperature emission, what do I mean? So anything that's at a physical temperature emits radiation in a broad spectrum that we call a black body spectrum. And that spectrum doesn't really change shape, but it changes peak, where most of the radiation is, depending on the temperature of the source. So if you have a very hot star, say a white dwarf at the center of a planetary nebula that's at 100,000 degrees, that's going to emit most of its radiation at ultraviolet wavelengths. Stars like our sun, which is about 6,000 degrees, are going to emit most of their light at visible wavelengths. Our eyes actually adapted to the sun. That's where most of the sun's energy is. That's where our eyes work. That's why we call it visible. At the opposite end of the spectrum, if you look at some of those clouds of gas and dust that I talked about, they're kind of 20 Kelvin, 30 Kelvin, just a few degrees above absolute zero. And so they emit most of their light out at very far or even millimeter wavelengths. And then, of course, the cosmic microwave background's at 2.73 Kelvin. And so that's definitely out in the this millimeter range. That leaves that red curve in the middle, what I call the mid-infrared. And the Earth, the atmosphere, astronomers, your telescope, they all emit at mid-infrared wavelengths because we're all at 300 Kelvin, 20 degrees C, 68 Fahrenheit. That's where the bulk of the radiation is. So trying to observe in the infrared is like observing in broad daylight with a telescope made out of light bulbs, just because everything is glowing. If you go out during the daytime and look up at the sky, you can't see stars. Why? Because the sky is scattering a lot of sunlight. If you got rid of that, you'd be able to see the stars. The problem is if you got rid of the atmosphere, you couldn't breathe. So you can't get away with it. But that's one of the primary reasons why observing in the infrared from the ground is so hard. Just everything is glowing. The other problem with the atmosphere is that the transmission varies wildly as a function of wavelength. And this is actually a good thing for us because if you look at the transmission, you'll notice that 2.8 microns, 6 microns, 17 microns, the atmosphere transmits very little light. And the reason is that molecules like water and carbon dioxide absorb most of the radiation that's coming through. And so, the Earth the atmosphere is just opaque at these wavelengths. We can actually use that. The meteorologists love it because if you've ever seen an image that looks like this, This is the water vapor content of our atmosphere. You see it from all the weather satellites. And so this tells us where there's a lot of water vapor, where the storms are going to be. So in this case, Southern California is reasonably dry, but there's something blowing through Arizona. So this tells us where all the water is. So the astronomer's curse is a meteorologist's blessing, but that's the way it is. So anyway, these are reasons why we want to put telescopes in space. So we're above the atmosphere, we're out of the range where everything is glowing. And that's why Spitzer and the Webb in particular exist. The other problem with infrared, with detecting infrared, is the detectors need to be colder than the characteristic radiation you're trying to find. So if you're trying to detect objects that are 30 Kelvin, that means your detectors need to be colder than that. And then there's some semiconductor reasons why you have to be colder still. So the detectors in my instrument, MIRI, actually have to operate at 6 Kelvin, 6 degrees above absolute zero, in order to behave themselves, which makes them very expensive. So between the atmosphere, the challenge of the detectors, infrared astronomy isn't easy. But we are building Webb. Well, let me put that in the proper context. We have built Webb. It's done, finally. So Webb Telescope is essentially a 6-meter infrared optimized telescope. It has 4 instruments that cover the wavelength range 0.7 microns, which is approximately red. You can just about see that with your eyes, all the way out to 28 microns, which would correspond to objects that are about 100 Kelvin. It's a partnership between NASA, the European Space Agency, and the Canadian Space Agency. So lots of good international partnerships. And it'll be launched on an ESA Ariane 5 rocket. So we're going to launch from Kourou later this year in French Guiana. So there's the telescope all folded up. When I gave a version of this talk 4 years ago, I showed a little animation of everything unfolding, but I thought, hey, I can actually show real hardware kind of unfolding the way it's supposed to. So 4 minutes after launch, this is what Webb will look like. It's just gotten rid of its fairings. It's out of the atmosphere. We're starting our cruise phase. And so everything's all folded up. And so you can see some of the mirror segments. You can see some of the sunshade all folded up. So that's what it looks like as soon as it comes out of the rocket. 30 minutes later, we start to unfold the solar panels so that we can shift from the battery, which keeps us alive through launch, and start generating our own power. After 3 days, the sun shield starts to deploy. So these kind of purplish color foil things start unfolding and flattening out. The yellow stuff you see here is all ground support equipment. It's not strong enough to fight gravity, so we have to help it a little bit. But they start folding out. And after 9 days, so it takes 6 days to do this, the sun shield will be fully deployed. If you look carefully, there's 5 layers of reflective material. So at the bottom layer, toward the ground, that's the sun side. So that's at 300 Kelvin, but at the top layer next to the telescope, it's actually only 40 Kelvin. So each of those layers helps shield the telescope from the previous layer until we get the temperature that we want things to be operating in. Right after that, we unfold the secondary mirror. And yes, this is a weird looking picture because it's on its side. I mentioned that pesky thing of gravity. We actually can't unfold the secondary mirror as it would in space vertically because it's not strong enough to overcome gravity. So they actually have to put the telescope on its side and help support the secondary mirror with a crane to unfold things. But on day 10, that's when the secondary mirror pops out. And then the next couple of days, we start moving the wing mirrors into place so that we end up with a fully hexagonal shaped primary mirror. So this is day 12 is when what I call the left side unfolds. Next day, day 13, the right side comes into place. And then day 14, so 2 weeks after we launch, we finally have a fully assembled telescope. And there, I explained this on Monday during our dry run. There's actually no picture of the Webb telescope with absolutely everything deployed like it will be in space. Again, thanks to that pesky gravity, we just can't unfold everything all at once. So you have to pretend that the sunshade is extended and the secondary mirror is out and all that. But anyway, this is kind of what it looks like when it's unfolded. Now that's day 14. We actually get to our orbiting point called the second Lagrange point after 3 weeks. So it's actually doing all this unfolding as the spacecraft is cruising from Earth to the second Lagrange point. Lagrange points are a nifty side effect of gravity when you have things rotating and revolving around each other. There are 5 spots where the gravity of the sun and of the Earth balance the tendency of the spacecraft to go flying off into space. The first Lagrange point is actually in between the sun and the Earth. It's about 1 million miles away from the Earth. And there are a few spacecrafts, like some of the solar observing spacecraft, that sit at L1 because it's a good vantage point to look at the sun without having to worry about the Earth getting in the way. The second Lagrange point is about 1 million miles outside from the Earth. And there have been a number of missions already. The Planck and Herschel mission, which actually I think this is a picture of, we're out at the second Lagrange point. So you can imagine it's like everybody's tied on a thread, and the spacecraft is just swinging along with the Earth as it rotates around the sun. The third Lagrange point is completely useless from our perspective because it's on the other side of the sun. So we'd be perpetually trying to look into the sun to see our spacecraft. So that's a non-starter. L4 and L5 are really interesting. If you draw a 60-degree equilateral triangle, you have a leading Lagrange point and a trailing one. Unlike L1, L2, and L3, which are what we call saddle points, so you can imagine if you put a marble on the saddle, it can fall off one side or another. That's the case at L1, 2, and 3. But L4 and 5 are kind of like very shallow bowls. And so you could put something there and it'll stay there. Jupiter actually has 2 families of asteroids called Trojans that are on either side of, 60 degrees separate either side of Jupiter, as sitting at the L4 and L5 Lagrange points. Earth, we know of exactly one that's at the L4 point, and it probably won't stay there very long because gravity from other objects like Jupiter perturb it and will eventually kick it out. But it's kind of interesting that there are these 5 relatively stable points. So it's a good place for us to park JWST. Okay, a little bit about the instruments, and I won't spend too long here. NIRCam is the primary near-infrared camera. Works from wavelengths from red to about 5 microns. It can take images. That's its primary job. It also has what we call coronagraphs, and I'll explain that in a second. It allows us to also do some very simple spectroscopy, and it's actually used to help align the mirrors in the telescope. So it's got a really important role there. So in terms of imaging, because it's 2.5 times bigger than Hubble, it will give us a 2.5 times sharper view. So galaxies that are kind of fuzzy blurs with Hubble, we actually expect to see some of those little bright star-forming spots down in here. So it lets us see more detail simply because it's bigger. A coronagraph is an optical device that allows us to block light from a very precise spot so that we can see stuff around it. So a coronagraph is used to block out the light from a star. And in this case, we can see these big, this sort of a disk of material around the star. This is Beta Pictoris. And so we can see it's got all this dust in the plane, kind of like the zodiacal light around the Earth. With better coronagraphs, we can actually see closer to the star than this. And in fact, if we do that, we see this little white dot next to the star along the plane of Beta Pix solar system, if you will. And so this is, in fact, a planet that orbits around Beta Pix. So we can take direct images of planets using these coronagraphs. And in fact, the European Southern Observatory redid this experiment 6 years later, and you can see the planet on the other side of the star. It's pretty cool. So it has a 12-year orbit, kind of like Jupiter. So it's pretty neat. NIRSPEC is the primary near-infrared spectrograph. This is a really complicated beast, but it allows 3 modes of spectroscopy: microshutters, an integral field unit, and then the standard fixed slits for spectroscopy. So what do I mean by microshutters? So at the image of the left is an image of a field of galaxies, and say we want to get spectra of 3 of those galaxies at the same time. In front of the spectrometer, there's what we call a microshutter. It's a grid of tens of thousands of little windows that we can open and close to let light through to the spectrograph. And so we can electronically control those shutters, and we close most of them and just open a few that correspond to things that we really want to get spectra of. And by doing that, it lets us get spectra of multiple objects all at the same time. So, if you're looking at a galaxy cluster near the edge of the universe, you can get up to 100 spectra simultaneously. It expands our ability to gather tons of data all at the same time. So rather than doing them one at a time and having to move the telescope in between, this allows us to get spectra of many things all at once. The second mode that I mentioned is called an integral field spectrometer. What this does is it allows us to take a spectrum of every spot on a small spot on the sky. So here's an image of a galaxy, and we have slices where each slice is pointed a slightly different direction, so that the light from slice number 1 will be spread into a spectrum on the left-hand side, and then slice 2 next to that, and so forth until slice 6 on the far side. And so this allows us to get, as I said, spectra of every spot, which allows us to do things like this. Here are some images of galaxies, and the middle column is images just with the primary line of hydrogen that I mentioned before, hydrogen alpha. Well, by doing this spectrum of every spot on the sky, we can actually get Doppler shifts of every part of the galaxy. And so this tells us how the galaxy is rotating. So in the top galaxy, this part, the lower left-hand part of the galaxy is coming toward us, and the upper right part is receding away from us. In this galaxy, it's kind of edge on, so you would expect good motion. The bottom galaxy looks a little bit more face on, but even so, we can still see that the bottom part is actually coming toward us, the top part is moving away from us. And it lets us understand a little bit about the dynamics within the galaxy. So this is an integral field unit, and it's important if we go. The fine guidance sensor, I can't even remember what NIRIS stands for, is another near-infrared instrument that does some very specialized spectroscopy in particular, and some imaging. One of the things that it can do is it has 2 gratings. So we get spectra at different directions, 90 degrees offset, but it allows us to get spectra of all the sources in this field of view. But if you have a case where 2 sources overlap, if you do the spectrum again with the other grating that's 90 degrees opposite, you can separate them. And so it allows us to get a spectrum of almost everything in this field. It's not quite as sensitive as NIRSPEC, because NIRSPEC eliminates the background light near the object that you're looking at. This doesn't, but it allows you to get everything. So there are benefits and disadvantages to both ways of pursuing it. But having this instrument gives us a lot of that gives us a lot of extra flexibility. And then finally is the best instrument of all, the mid-infrared instrument. This allows us to do imaging from 5 out to 25 microns. It has coronagraphs. It does spectroscopy. It does everything. So there's only one mid-infrared instrument. So if we want to do it, we have to do it all. So we also have slit spectroscopy, and we also have an integral field unit spectrometer as well. One of the roles that I had was the development of the detectors, the sensors that we use in the system. And every time you see a picture of MIRI, they hide my detectors on the back side, which is really bothersome. So in a little bit of gratuitous self-promotion, here's a picture of me in a bunny suit with Kalyani Sukatmi, who was our product manager at the time, holding one of our detector units. So this is one of the things that I actually did. I actually got to touch. So why do we have a mid-infrared instrument along with the near-infrared instruments? Why do you need different things? So one of the things that the near-infrared instruments will do is allow us to see ultraviolet light from very distant galaxies that's been redshifted into the near-infrared. But if you want to look at visible wavelength light from those galaxies, that gets redshifted into the mid-infrared. So the near-infrared instruments will see the redshifted ultraviolet. We get to see the redshifted optical. And that's important because we understand galaxies best at visible wavelengths. So MIRI gives us a chance to see those for the highest redshifted galaxies. The near-infrared, we tend to see mostly spectra of atoms and molecules in high energy conditions for things like nearby stars and so forth. In the mid-infrared, we see molecules at lower energy conditions. So like the water ice, carbon dioxide ice, those are all things that show up very nicely in the mid-infrared, whereas we tend to see things in the gas state. So gaseous hydrogen, molecular hydrogen, or gaseous water vapor shows up more in the near-infrared. In the near-infrared, we tend to see more mature stars. They're the ones that are still forming planets, so that's still very interesting. In the mid-infrared, we see very young stars where the stars themselves are still forming. They're so young they haven't started forming planets yet. It's still the stars that are picking up all the mass. And then finally, in the near-infrared, that's where we see these very hot planets, the so-called hot Jupiters, very close to their stars. In the mid-infrared, that's where we'd be able to see more distant planets that are at more Earth-like temperatures. So if you want to try to find Earth 2, you're better off doing it at mid-infrared wavelengths. So all the instruments important, we complement each other, and so it's a good crew to have. And then I just have to say, I mentioned that JWST was an international partnership. MIRI itself is a 50-50 partnership between NASA and ESA. So JPL and our contractors contributed the US half. And then there are 24 astronomical institutes in 10 countries contributing the European half. And I like this graphic. It's all 11 flags of all the countries that have contributed. Brownie points if you can figure out what all the flags are. Okay, so what do I want to observe with Webb? What does Mike Ressler want to do with this? As mentioned at the beginning, I've been working on this thing for an awful long time, pretty much the bulk of my professional career. So what do I actually want to do with it? Well, I have a little bit of guaranteed time that's mine to do with as I please. And so I developed 6 small programs to explore, different things that I'm curious about, or that some of my colleagues that I've worked with for a long time have been curious about. But one of them actually has a San Diego amateur, in quotes, because it's still me, amateur astronomy connection. And so I thought that would be a little bit fun talking about. I love camping. I love camping in the Anza Borrego Desert. Particularly the Yaqui Well Primitive Campground is one of my favorite spots. And so over January 1st, 2000, remember Y2K and the world was going to come to the end. So we decided to go camping. I have a little 10-inch f4 Dob telescope, and I have a pretty wide field eyepiece that I got for it. And so I'd been looking at the California nebula, which you cannot look at all at one time, even with a 2-degree field of view. But with the nebular filter, you can kind of see lumps and bumps and convince yourself that you're not imagining things. And so when I was finished with that, I just kind of kicked the telescope around just for fun. And I saw a star that had this fuzz around it. And I thought, I must be getting tired. Why does this star look foggy? Well, I found a sketch that a gentleman named Richard Orr did, which looks remarkably like what I saw in the eyepiece. So what I remember specifically is there are 3 stars of pretty much the same brightness, but this middle star had some fuzz. And that's what convinced me I was actually seeing something. I wasn't just getting tired, my eyes getting blurry. So I had rediscovered the planetary nebula NGC 1514, sometimes called the Crystal Ball Nebula. With a big telescope and long exposures, you'll see something like this. But I was also a science team member of the WISE All-Sky Infrared Survey mission. And early on, they said, hey, go look at your favorite targets, see what they look like in the infrared, see if you see anything interesting. So I did that. WISE works at the same infrared wavelengths that MIRI does. And when I looked at 1514, this is what I saw. And my first response was, holy mackerel, what is that? Definitely not what I expected to see. It's got these kind of 2 parallel rings around it. So just comparing them visible to infrared, the center inner shell, which is about 2 arc minutes in diameter, and the greenish stuff in the infrared here, they look pretty much the same. The only difference is the resolution. But these rings are just completely unique and something that I did not expect to see at all. And so I thought, hey, I've got guaranteed time with JWST. I can look at whatever I darn well please. I'm going to look at NGC 1514. So one of my little projects is to look at it. And some of the questions I have to answer, what are the rings made of? Are they the same stuff as that inner shell, or does the composition differ somehow? Is it mostly dust? Does it have a lot of gas in it? I just don't know. How are the rings expanding with respect to the rest of the nebula? We should just have enough ability to measure the Doppler shifts that we might be able to see, blue or red shifted spectra. Then did WISE measure the temperatures correctly? There are bright emission lines that we see in the infrared, and so because WISE was not a spectroscopic mission, just pure imaging, we're not sure if we got a good temperature or whether it's contaminated by those emission lines. And then just what do the rings look like with higher resolution? Are they really thin and narrow, or are they kind of broad and fuzzy like this? What do they really look like? So I do see a question in there. I'll get to that one in a bit. Okay, so that's one of the projects that I intend to do. And, oh, sorry. This might be really hard to see, and I apologize because it didn't turn out quite as well as it should have. But you'll notice there's a little square that I'm now popping up in and out at the center. That's roughly the field of view of the MIRI spectrograph. It's really tiny, but at this position, I can get the spectrum of the central source, which is really good. And if I move the telescope around, you'll now see scattered spots around the nebula. And so my intention is to look at places of specific interest to say, okay, what do I see here? What do I see here? What do I see over here? The MIRI imager and spectrometer can't take data on exactly the same spot at the same time, but you can run them both at the same time. And so what I found is if I get a spectrum of the central star, I can get an image of part of the nebula just off to the side. And if I pick my spots to get the spectrum properly, I can actually get, I can piece together an image of just about the entire nebula. I miss a couple of nips and tucks here and there, but by being a little clever and a little selective, I can actually get an image of the whole nebula as I'm getting spectroscopy of all these interesting places. So anyway, so that's one of my little projects. So current status, and this will come up to the launch date question. So all the testing is complete. The telescope's built, the spacecraft is built, it's been fully tested. The sun shield has actually been folded up for the last time. The mirrors right now, as we speak, are extended in their flight position for the very last time. And over the next week or so, they'll be folded up for the last time. Then there are a few cleanup activities to get done. And then we start boxing it up. There is a huge shipping container that this whole thing will fit into. Gets put into that shipping container, gets put on a boat down at Long Beach, and then it will sail through the Panama Canal over to Kourou and French Guiana, to the European Space Agency main launch center. In September, there will be one more observatory aliveness test down in French Guiana. So that's our last chance to turn things on really quickly to make sure everything is still good to go. And then early October, the observatory gets craned up on top of the Ariane 5 rocket. And October 31st, give or take a little bit, we'll launch the thing. So the question was, how sure is JPL that October will be the launch date? And what is the level of confidence that the setup process will go as planned? So October 31st is when we hope to launch. Our actual launch readiness date, meaning that we're ready to push the button, will actually be a couple of weeks earlier than that based on our current schedule and the progress we're making. There is the possibility of a little bit of a traffic jam down at French Guiana with other things that need to get launched. So I wouldn't be surprised if it was a couple of weeks, give or take, around October 31st. But as I say, at this point, we're really in our final wrap-ups. It's just sort of the final cleanup and get ready for shipping. So fingers crossed, there's not much that can delay us significantly at this point. It's been a long time. I'm so ready to get this thing launched. But it looks like the October date's pretty good at this point, give or take a little bit. There are plenty of online resources if you're interested in exploring things further. The top one is the main NASA website for JWST, pretty easy, jwst.nasa.gov. The European Space Agency maintains their own JWST website because it's a big chunk of their scientific portfolio as well. So they've got a pretty complete website. Space Telescope Sciences Institute in Baltimore is the facility that will actually be running Webb when it's doing its work. That's where we'll get all our data and all that stuff. So they have webtelescope.org, which is their public outreach website. Nothing about JWST is secret except for the very first publicity images that they're going to do. Those are under lock and key. They haven't told any of us what they're going to look at first. But all the actual scientific programs are publicly available. If you want to go look at what we're going to do for the first year, they're all at that STSCI website, including my NGC 1514 program that I mentioned. The link is kind of gross, so if you just search for JWST approved programs, you'll find the links that tell you everything we're doing. The other one, for just short video clips of activities, the mirrors unfolding, sun shield unfolding, all that kind of stuff. If you go on YouTube and just search for social media short web, you'll find a number of kind of 2 to 3 minute videos around various aspects of the observatory. So I find those all pretty interesting. So, as I say, feel free to go explore, figure out what the crazy scientists are actually going to use this thing for. But fingers crossed, we're almost there. So that's it. I'd love to take any questions. You've been a pretty quiet bunch so far, but anything interesting or I need to clarify, please let me know.
I do have a question. Can you hear me?
Yes.
Is there any chance we'll see something we didn't expect in the spectrographic data?
Oh, absolutely. I guarantee it. It's funny, missions like this, we always have our supposed science themes. And the science themes are important because that's what we use to tell the engineers, this is what we need to be able to do. And so the spacecraft is designed to do that. But the real fun is the stuff that we don't expect. That NGC 1514 Planetary Nebula, no clue there was anything like that, completely unexpected. But that's really what makes these missions worth doing. It's not the stuff that we already know about that's interesting, it's the stuff we don't know that'll knock our socks off, and that's what's fun. So I guarantee you that anytime we point a new instrument at the sky, we find things that we just did not expect. So we will definitely find stuff that we just couldn't imagine.
Dr. Ressler?
Yes.
Excellent presentation. Thank you very much. I have a couple of questions for you. The
Sure.
first one has to do with, I'm kind of interested in asteroids and comets in our own solar system, but also other solar systems. In our own solar system, we have an area called the Oort cloud, and we keep thinking there's a planet 9 out there, and we're always looking for comets that are hot that might be coming in for planetary defense. Can you comment on whether or not this telescope could be used for those two types of purposes?
So the short answer is not very well. And the reason is Webb has a relatively narrow field of view, and it takes a long time to move simply because it's so big and floppy. So Webb is really good at characterizing individual sources that we already know where they are. So if you had a Kuiper belt object that you wanted to characterize, or even Mars, Webb would be very good at that because it's something that we can track, we can focus on. For surveying the sky, trying to discover new things, there are actually better things. So just to give a shout out to the Reuben Telescope, which is going to be surveying the entire sky every few nights from the ground. And there's another mission that I'm actually involved with that's in the early development phases called the Near Earth Object Surveyor, which will look for near Earth asteroids that are potentially Earth impacting, which also has an extremely wide field of view. So those wide field surveys are what you really need to try to find something you're not sure where it is. So if you're looking for a planet 9, or if you're looking for, just trying to discover new objects, those surveys are actually better. Webb is really designed to characterize things where we already know where they are.
Follow-up question. What are the chances we could look at Proxima Centauri and identify minor planets the size of Vesta or Ceres, or even an asteroid belt in that particular solar system?
So I don't know about Proxima Centauri, but I unfortunately have to admit that I'm a co-investigator on a proposal that will be looking at Alpha Centauri for exactly what you're looking for. So when I was first approached about this proposal, I kind of face palmed and shook my head and say, we built the biggest space telescope ever to look at the faintest objects in the sky. And what do they want to do? They want to look at the 10 brightest stars. I just can't believe it. Go use another telescope. So yeah, I mean, there are hints that Alpha Centauri does in fact have at least one planet around it. And so, this is sort of a highly specialized observation where we'll look to see what's there. So using the coronagraphs, we can look at ridiculously bright stars. And so this set of observations will be doing exactly that, using a coronagraph to see what's in the proximity of Alpha Centauri. I was just going to say, I don't think there's any reason why you can't do Proxima Centauri, but at least for right now, they decided Alpha was the one to go after.
Sounds great. Last question. How long until we can see data actually occurring for public access on planetary data systems or NASA's databases?
So there's a series of programs called Early Release Science programs. You can see what they are on the links that I mentioned. The data from those programs goes public immediately. So the day, roughly a day after it's downlinked, you'll be able to go onto what's called MAST, the Mikulski Archive for, I forgot. Anyway, it's masked. It's part of Space Telescope's database, and anyone can download data as soon as it's there. Most of the programs, like my little guaranteed time programs, I actually have a 1-year proprietary period, or sorry, I'm not allowed to call it that anymore, a 1-year exclusive access period. But after that 1 year, then all that data goes public as well. So it depends a little bit on the program, if there's an exclusive access period, but at least some will go public right away because we want other astronomers to be able to look at it and find out how Webb actually works, so that when it comes time to do the second year's proposals, people have a good feeling for how Webb is working and what it can and can't really do.
Wish you best of luck and thank you.
Thank you.
Mike, I had a question about the old days when it was NGST, and I worked on NGST for Goddard back at the beginning. I wonder what you were doing back then.
So in the introduction, there was actually one slight inaccuracy. I actually started in 1997. There was a call for proposals for concept studies for instruments to fly on NGST. And that's when I got in the game. A colleague and I put in a proposal and we were actually selected. And between the concept study, some early technology development, and then the MIRI instrument itself, I've been working on some aspect of JWST since 1997. Before that, I had worked on ground-based infrared cameras that we took to the Palomar 5-meter, as well as to the NASA Infrared Telescope facility and the Keck 2 telescopes out on Mauna Kea. So I kind of transitioned from the ground-based stuff into JWST sorts of things. So I wasn't involved until 97, but I've been a thorn in people's side ever since.
Thank you. Another question is, where is JWST right now? Is it at Space Park, or is it?
Yeah, it's in the huge M8 clean room at Space Park, so Redondo Beach. And if it weren't for COVID, it would be a little bit easier trying to get a peek at it. But at this point, everything is really, really locked down. So I can't even go in and have a look anymore.
Thank you.
Yeah.
Mike, how long is the first mission? What's the time that we expect to have JWST in space for its first mission?
Okay, so officially, the required lifetime is 5 years. Its goal is at least 10 years. There's enough propellant to go somewhat longer than 10 years. And there's nothing else in the observatory that we think is particularly life limiting. We've got momentum wheels and that kind of stuff too. So those are always the bugaboos. But the 3 near-infrared instruments are all passively cooled, so there's no cryogens to run out for them. MIRI uses a mechanical cryocooler instead of solid hydrogen or liquid helium like previous infrared missions. So we don't have anything that's going to run out either. So it really is the propellant for the observatory that's going to determine the lifetime. When the propellant's gone and we can't steer anymore, that'll be the end. But hopefully that'll be well over 10 years down the road. See, I guess I can stop sharing my screen. How do I do that? Yeah, there we go. Right.
All right, folks, other questions?
What is the object in the center of the mirrors? It's a black pyramid-shaped object with some kind of a panel on the end of it.
Yeah, that's primarily just a light baffle. There are some other sensors there to, figure out the health of the telescope, but it's primarily just a light baffle. It's a typical Cassegrain style design. Light comes in, bounces off the primary, up to the secondary, and then back in that central hexagonal hole in the middle. So yeah, it's just light baffle for stray light control. Yeah, there is no, unlike Hubble, this has no shield around the whole telescope. So, some of the, big Dobsonian telescopes that, you just see the mounting struts. There's nothing that actually surrounds the cylinder. We're wide open to space. So things like that little snout are what we use to help keep the stray light down.
What's the total weight of the telescope?
Total weight's about 6,200 kilograms. So it's not a light, it's not light, even though we did our best to lightweight everything. There's a lot of observatory there, so it definitely needs a heavy lifter. I will say the ESA Ariane 5, after the first 3 or 4 launches, has an impeccable launch record. They've gone something like 75 or 80 launches in a row without incident. So it's a pretty reliable vehicle. So hopefully that record will continue.
Question.
Yes.
Given the fact that it's a Lagrangian point, how likely is it to be hit with debris and possible asteroids and things of that sort?
So at the second Lagrange point, we actually don't sit at one spot. We actually go in what's called a halo orbit around the Lagrange point. So it's an orbit, if this is the plane of the solar system, JWST will actually do an orbit kind of like this. And it's something like 6 months to do that orbit, if I remember right. So we don't expect to have any issue with any other man-made debris. Now, micrometeorites are definitely going to be a problem, or, well, I shouldn't say a problem. They will definitely be an issue. We do expect micrometeorites to hit the sunshade and poke holes in it. So eventually the sunshade's ability to baffle the telescope will degrade over time. We don't expect it to be so bad that it will prevent anything before we run out of propellant and that sort of stuff. But we do expect impacts from small high velocity particles. So we do have a pretty good handle on the environment based on other spacecraft that have been there. So we kind of know what to expect, and designs have been done and expectations have been set that are consistent with that. So yeah, could something have our name on it? Sure. That's always an issue. But barring truly bad luck, we should be okay.
I have a question.
Yes.
Those mirror segments, are they articulated or are they fixed?
Each segment is on 6 actuators. So kind of like the Keck telescopes that have actuators that tip and tilt the mirrors. We also have actuators. We don't have to control them on a 30 hertz cycle. We expect days between adjustments. But yeah, each mirror can be tipped and tilted slightly with respect to everybody else to achieve appropriate phasing so that all 18 segments work together as one mirror. So they're kind of fixed, but there's still some motion that we can allow things to get tuned up. We don't expect things to change much once we initially set them, but as we point around different parts of the sky, the sun shield moves a little bit with respect to the sun and the earth, and so we expect the heat loads on the telescope to change a little bit, and so we might need to do some tuning because of that. But by and large, once we get them tuned up, they stay there, but we have the opportunity to tune a little bit just in case. It's one of my cats who loves video conferences.
How does the telescope move from one object to another?
So mostly reaction wheels, pretty much standard stuff. So you use a momentum of reaction wheels to help push the telescope around. When too much momentum builds up, the wheels spin too fast, and we use a little bit of thrust to rejigger things and slow stuff back down. So momentum management is a big deal, but that is how we point the telescope, by using that angular momentum to help push the telescope.
I have a question.
Yes.
First I want to know what your kitties names are.
So there's one of them right on cue. So this is Tila. So she's a Bengal cat. We have another Bengal cat named Snickers. And then we have a third mutt. His name is Nixie. We also have 2 flat-coated retrievers, so 2 big dogs. So our house is always a running circus, but we like our critters. So
I love kitties.
we had a bear. We had a bear in our backyard 2 nights ago, so we have a little bit of everything.
Oh my goodness! I was wondering, the NGC 1514, does it have a different name besides just the technical name? Does it have a? I like to try to learn the fun names of the Messier objects.
Yeah, so it's sometimes called the Crystal Ball Nebula.
Okay,
because it's a little cloudy and murky, I guess.
Right. Okay.
So the central star is actually quite easy to see. It's kind of a 9th magnitude source, so pretty much any amateur telescope will at least allow you to see the central star. Seeing the nebulosity, as I said, 10-inch daub in the middle of the desert with a narrowband filter, is still pretty hazy. But if you look at it, you start to see some of that mottled appearance. So it's well within a decent amateur-sized telescope if you've got a good dark sky.
And you probably maybe you already addressed this, but how come we can't call it James Webb? What's up with that?
It's too formal. We don't call it the Edwin Hubble Space Telescope. It's just the Hubble Space Telescope. So or even Hubble Telescope, I guess, is the official preference. And so that's why they wanted to shorten it down to Webb Telescope. But to me, it will always be JWST, James Webb Space Telescope.
Right.
Just because I've been working on it so long.
I can't get away from it. It's James Webb. And one stupid question. I'm not as advanced as everyone else, but you were talking about the CO2 levels. I was just curious, the Van Allen radiation belts. I know there's different levels of the atmosphere and all that, but does that have any protective variations? Like, is there any protection that it gives to the CO2 levels, or is that just non-existent?
They're really too far outside our atmosphere generally to have much direct influence. And JWST will be well past the radiation belts. We're actually 4 times the distance of the moon, so we're way outside that stuff. So general, they're pretty separated. Not much influence on each other.
Yeah, I know that James Webb is way out there. I just when you were talking about the CO2 levels in the Earth, and it just came to my mind, like I was wondering about the radiation belts and if that has any effect on them, if it helps at all.
Yeah, the lowest radiation belts are still, the lowest radiation belts are still 300-400 kilometers up, so they're well above any significant atmosphere.
Oh, okay. And I also want to say thank you so much. This was so interesting. Thank you.
Thank you. It's a lot of fun.
Hey, Mike, the Kepler telescope, its main demise was those reaction wheels. How many reaction wheels does Webb have, and will they last a long time, or have they upgraded them somehow from Kepler's wheels?
Yeah, unfortunately, I don't know that much about the innards of the spacecraft itself, and they're definitely a spacecraft thing, so I can't give you a real answer. I know they're definitely bigger simply because we have more mass to throw around, but unfortunately, I don't know the number or what their heritage is, what kind of life testing they've had. So that's one I'd have to go look up. Sorry. So at least there was one question where you got me.
I have a question. Do you think SpaceX could service it if it needed fuel or replacement reaction wheels?
So it's 1 million miles out, which makes it really, really tough to get to. However, by congressional mandate, it actually does have a grappling assembly where some putative spacecraft at some point in the future could be designed to mate up to it. But there are no real plans for servicing at this point. It's just too far away. And because I'm going to violate my own rule and talk just about cost for just a second, that is one reason why JWST is so expensive, is the amount of testing that it had to go through to prove that we haven't screwed anything up. Really does get expensive in a hurry. But knock on wood, whatever superstition you might have, we have tested our way past all that stuff. But we'll find out in November 2021 how things really look.
Steve, you got a question?
Yeah, I was just going to ask a couple things. So are there any kind of monitor cameras that can actually look at the telescope itself, send images down, like for kind of health checks at all? Or I know there's a ton of telemetry probably, but
there is a metric bucket load of telemetry, but sadly no cameras. I can't believe they did that. It's like, come on, you can put a couple of webcams out there, even if they die, it'll be enough to tell us that everything's where it belongs.
I've been wondering that for a long time. But another thing, so you worked on the sensor, you designed some of the sensors, or the sensor for the mid-infrared?
Design is too strong a word. They were actually developed by Raytheon Vision Systems out in Goleta, California. But I was the contract technical manager and detector scientist, so I got to tell them what to do.
Can you talk just real briefly about the sensors? Are they CCDs? Are they bolometer? I mean, what for infrared? I mean.
Yeah, so these are arsenic doped silicon detectors. So they're reminiscent of silicon photodiodes, except they use a little bit of arsenic as a dopant to make them sensitive to infrared rather than visible wavelengths. And so it has what we call a direct readout. So each pixel is addressed separately. It's more like the CMOS sensors in digital DSLRs.
Right. I was going to ask, are they similar to an EMCCD?
Yeah, so definitely not CCDs. These are more like the sensors in your SLRs. But yeah, if you Google a little bit, you can find out more information, maybe even a paper or two by me if you search hard enough, if you're interested in more about them.
Sure.
Is it a hybrid? Is it a hybrid structure that's bonded to silicon?
Yeah. So the arsenic doped silicon is basically a 1 square inch slab of material. Well, it's got its own layers. There's a pure silicon layer, and then a 30 micron thick layer of the arsenic doped silicon, and then below that we indium bump onto a cryo CMOS readout circuit. And I'm probably violating ITAR if I say too much more, but yeah, it's a fairly common design, especially for infrared sensors, where you have the infrared detector layer, which is some exotic material, and then it bonds to a silicon readout device.
Okay, I got a crazy question. Oh, I'm sorry.
Go, Jerry, go.
A quick one. Hey, can we look at black holes with this thing?
We can look at material around black holes with this thing. Certainly somebody's going to look at the black hole in our own galaxy center. What we'll see is a lot of the gas and dust that's spiraling in around it. They're actually, it sounds kind of funny, but I mentioned I built a ground-based mid-infrared camera that we used at the Keck telescope. And we used that to actually get mid-infrared images of the center of our galaxy. And so you see these big spiral arms, many parsecs in size. So, they're huge compared to the black hole itself. but we see all sorts of lumps and bumps and so forth in there. Because Keck is a 10-meter diameter telescope and Webb is only 6 meters, we actually got higher resolution images from Keck than we will from JWST. And everything in the galactic center is so bright, we're actually limited by the signal that we're getting from the galactic center, not by the telescope or whatever. So JWST isn't going to be any more sensitive for that particular observation than Keck was. So that's sort of a special case. Now, black holes around other galaxies, or even other black holes in our own galaxy, like SS433 or Cygnus X1 or something like that. In the infrared, we really don't, compared to other techniques, we don't get as much information about the black hole itself, but we can get information about material that's spiraling in around them. So I don't know if anybody has proposed direct observations like that for cycle 1, but somebody will do it sooner or later. So yeah, it'd be interesting.
So the Hubble Deep Field, I think, was many days of exposure.
Yeah.
What's exposures typically for this telescope?
So we're going to have some of the same, many hours looking at blank spots in the sky just to see what's there. Exposures, obviously vary tremendously based on, what kind of source you're looking at, how bright it is. The ones in my own programs tend to be 5 to 20 minutes, but that's just, the stuff that I'm interested in. There'll be some that are just a few seconds, and then there'll be others that are days. I know a couple of the biggest programs that were selected for cycle 1 are, in the couple of 100 hours. So, a week, 7 days is 168 hours. So I think the biggest ones are about that time scale. Now, I don't think, some of those might be one field for just about that long. I have to go back and look at some of the details, but yeah, it's, NASA has already invested heavily in some of these deep fields. And so they're going to continue to bang away with them with the Webb telescope as well. And they will get days of time. Anything else?
Everybody sounds awful quiet out there.
Yep. Maybe ran out of steam.
I have a silly
Mike,
question. I got a goofy question, but how in the world do you secure that huge heavy telescope for all that transport? And check it that it's come through the transport safely.
Lots of bolts. Yes. So there is an enormous shipping container nicknamed STARS. I think it's got 2 R's in it or 2 S's. I don't remember. But it is big enough to hold the full observatory all folded up. It's got sort of the air ride equivalence, but they are literally taking it by truck down to Long Beach, and it gets loaded on a ship, which I actually have heard the name. We actually know which ship we're going on, but I don't remember off the top of my head. But yeah, we're going by boat, through the Panama Canal, and around to Kourou. I mentioned there is an aliveness test once we're down in Kourou, so that'll check all the basic things to make sure that we didn't knock any cables out of whack or something like that. So it'll be enough to let us look for the basic boo-boos. Obviously, we don't think that will be an issue. We have to survive launch. We ought to be able to survive a boat. But as I say, there is one last aliveness test after we're there, before they light the candle.
Well, thank you for the great presentation and your tremendous perseverance through all these years developing this. I know what long projects are like, and just a fabulous accomplishment.
Yep, I am very eager for October to get here.
Bet you are.
say, Mike,
Yes.
I heard, I read on the internet that the ship it's going on is its name is Titanic. And the
No, definitely not.
the captain's name is Jonah, but I don't know his last name. So
I can assure you it is not named the Titanic. Yeah, I can assure you it's not named the Titanic. I think it starts with an M if I remember right, but I have to go look it up.
Dennis, you're bad.
Actually, the funny thing is I have learned that, you know, thanks to Google or somebody, you can actually look up positions of ships, you know, same way you can track flights on radar, there are maps that track ships. And when they first told us what ship we were going on, I looked it up and found out it was in port in Marseille, Marseille, France at the time. So it gets around. But
just curiosity, Mike, where's mission headquarters? Is it JPL or is it?
No, it's Space Telescope Science Institute in Baltimore. STSCI is actually officially part of Johns Hopkins University. So they're under contract to run it for NASA. So JPL has had two primary pieces of involvement in JWST, and that was, you know, the US half of the MIRI instrument. And then some of our optics designers were actually involved in the early telescope design. Manufacturing and all that was Goddard's responsibility, but some of our guys were involved early on. JPL with the Infrared Processing and Analysis Center, you know, that was the data center for the Spitzer Space Telescope. So, you know, we have done a lot of infrared astronomy here at JPL, but this is primarily an East Coast thing. So Goddard is the main center responsible for JWST. And then Space Telescope Science Institute is the operations center. So that's where the mission control rooms are. It's where the data is being hosted. So they're the primary drivers, and then we help out when needed. And I will say I'm going to be spending more time than I care to. 3 weeks after launch is when we first turn on MIRI for the first time. So I'll be at Space Telescope for those commissioning activities to say that, you know, MIRI survived, it's ready to get cold. And then 3 months after launch is when MIRI is finally at its operating temperature. And so I'm responsible for a bunch of activities when we first turn on MIRI when it's cold, you know, again, to show that it's fully operational and it's ready to start doing science. So I'll be spending quite a bit of time in Baltimore before all is said and done.
At what point in time do you bow out, if you will, as a project coordinator, project manager? Do you, at some point in time, I assume you get to go find another toy to play with? Yeah. So officially on the books right now, I'm employed by JWST until launch plus 1 year. So if we launch October 2021, I'm officially on the project until October 2022. That may move a little bit depending on how things go. Hopefully things will go smoothly and that will really be the date. But as I mentioned, I'm working a bit and will ramp up more on this near Earth object surveyor. So once I start ramping down from JWST, then I'll start to go hunt for asteroids. So yeah, it's one thing after another, but that's good. It'll be a little different from what I've worked on all this time.
My question.
Yeah.
This Ariane 5 will get you to, I guess, the near Earth orbit. And so how does it get kicked up all the way up to L2?
Actually, the Ariane will get us all the way there. You know, it blasts us off, gives us some momentum, and then we kind of cruise the rest of the way. But it gives us enough velocity that's it. There's no propellant. There's no major thrust on the spacecraft itself. So we are depending on the Ariane to give us everything we need to get us there. There are a few course corrections along the way. That is some of the internal propellant. But the real thrust is all provided by the Ariane 5.
How close to the launch date do you start getting really nervous?
I'm already nervous. it's funny. I've been working on this thing for all these years, and I have these science plans I want to do. But I'm looking at it and say, oh my God, they're going to start observing in a year, which means I have to figure out how I'm going to reduce the data and how I'm going to interpret it. And do I need to hire a postdoc to help me out? So it's already begun. But yeah, the real terror will be getting the telemetry that's telling us the telescope is unfolding, since we can't actually see it. Yeah, so Mars, they talk about 7 minutes of terror. That's nothing. We got 3 weeks of terror. What are they worried about?
Anybody got anything else? I don't know. I had a whole bunch of questions I kind of forgot about. One question I did have is that let's just say in 6 months or 7 months worth of time, you're going to be able to rejoin us and tell us all the fun things you've discovered?
I would say in about a year, I'd be happy to. So what I didn't say was that after launch, it actually takes us 6 months to commission the whole observatory. So there won't be any proper science until 6 months after launch.
Oh, wow.
So about a year from launch would be about as soon as I'd have something really interesting to say. But yeah, I'd be happy to come back. I like talking about what I do. So if it interests you guys, I'd be happy to do a repeat or not a repeat, a reprisal.
Talking to a bunch of people here that run around at nighttime with telescopes. There's a lot of interest here.
I hope so. I hope so.
I'm really impressed that you have your own telescope and you can go out and do what we do. That's just awesome.
Hey, what got me into astronomy was a 6th grade class camping trip where the teacher had a little, it's probably a 60 millimeter refractor, and he showed us Saturn in it. And I can still remember the view of Saturn and its rings through that goofy little telescope. So I've been into this for a long time. And I grew up in Pennsylvania, and I was out in the winter when it was 10 degrees outside. So, I went through all that as well. And I was lucky enough that I could make a career out of it. But yeah, I still like getting outside with my own scope. I will say my job has no electronics. It's just me in the sky with a big hunk of glass in front of my face. So all the electronic controls, that's too much like work. I don't do astrophotography either, because that's also too much like work. It's my chance to just use my eyes.
Well, at some point in time, we got to have you down to our dark sky site down at Tierra del Sol. So when you're getting tired of running around LA, we've got 10 acres on the Mexican border where yes, there's telescopes, but there's the occasional cigar and scotch and whatever else happens to sneak out at nighttime under the stars.
Right. Yeah, might have to take you up on that sometime.
We have a 22-inch that we use visually. It's a Ritchie Creechin, just visual. Great eyepieces. Come play.
Now I'm drooling.
All right. If anybody's got anything else, well, thank Dr. Ressler for doing his job. That's outstanding stuff. I'm still going to pick his brains about Hawaii, because I was over there for a while trying to look through telescopes, and the folks at the Telescope Institute there didn't want anything to do with me, which I wouldn't have felt was.
Oh, I've got a visual observing experience that I guarantee you no one here can ever reproduce. One time while working at the Keck 2 telescope, they had its tertiary mirror in place and were bouncing the beam out onto the platform next to the telescope. And so I got to look at the moon and Jupiter through a 10-meter telescope, 400-inch telescope. So little naked eye observing. It felt like I was about ready to walk on the moon. It was, the moon was 6 feet in diameter. You just kind of stuck your face in there somewhere and focused on whatever piece of the sky happened to be hitting your face. Definitely interesting.
Fun stuff. All right, we'll call it an evening. Thank you very much, Mike. Great talk.
My pleasure.
Great talk, Mike.
A lot of fun being here.
You will hear from us again, I have no doubt.
Thank you.
Look
Thank
forward
you.
to it. All right.
Thank you.
Good
Thank you
night.
very much.
Thanks.
Good night, everyone.